Today's lesson is on the wave nature of light, part 3. You may remember that we have already discussed the different types of light waves there are. There are everything from gamma rays up to radio waves with huge differences in the wavelengths and the frequencies. But of course they all travel the exact same speed. Because again, light waves need no medium, as in difference to other types of waves like sound waves and water waves. And then yesterday we talked about how light can be polarized. It can only be polarized if it is a wave. Light, as it goes through space, whether it's in this room or in outer space, the light waves vibrate up and down and left and right and on angles in all sorts of different directions. And the polarizing filters we found yesterday can take that light wave and force it to go in one direction only. And that can only happen if light is traveling as a wave. Well, I want to take a look at one other thing today, and then we'll do something else tomorrow that deals again with the wave nature of light. So if light is a wave, it should be able to do all the other things that other waves do. Now, you may remember when Mr. Winter showed you this apparatus. In this apparatus, we had a buzzer in the middle here, and it sent out the same sound from this side and this side. So we had compressions and rarefactions coming out from here, and compressions and rarefactions coming out from this side. And where you were seated, we had the compressions and the rarefactions colliding, which we call interference. They interfere with one another. And wherever you heard a compression from this side line up with a rarefaction from this side, those two kind of canceled each other out. We call that destructive interference. And we heard a dim spot. And if you had a compression from this side line up with a compression from this side, we call that constructive interference. And in that spot, wherever your ear was, you would hear a loud spot. It's due to the interference, the destructive interference and constructive interference of those waves. Well, if I could make some sort of similar apparatus like this for light, what would you see? Take a second and talk to your physics friend about what would you see if I had a similar apparatus to this, where I had light waves coming out of both sides of whatever the apparatus is, so that the light waves could collide. If the light waves collided, what would you see? Take a second to talk about it with your physics friend. Go. Well, it turns out that I have just such an apparatus. I hope that when you discuss with your physics friend that instead of hearing loud spots and quiet spots, clearly that's not going to happen with light waves. They're not sound waves, they're different. Instead of hearing something different, you would see something different. And so an interference pattern for light waves looks like bright spots where there's constructive interference and dim spots where there's destructive interference. You might want to take a second to write that down in your notes. Again, where I have crests lining up with crests out again where you're seated, we'd have a bright spot. And if I have a crest lining up with a trough, I'd end up with a dim spot. And if I had a trough lining up with a trough, if those two collided and interfered, that would be constructive interference again, and I'd have a bright spot again. So let me show you this apparatus that does this for us. Here it is right here. It's a piece of glass with some really thin film between it. Let me show you closer. There it is. Hopefully you can see that on here I've got different spots where there are what's called double slits. And if I shine light onto these double slits, it takes that light and it separates it into two sources. Not that different than what I had here. Here I had the same sound coming out of two sources, two different sides. And here I'm going to have one laser light shining on this, and it's going to split it into two sources. Now it's important that I use a laser because it turns out laser light has the same, it is one constant frequency and one constant wavelength, if you want to think of it that way. And in fact, in this one, it tells us on this laser that the wavelength is 650 nanometers plus or minus 10 nanometers. You can read it for yourself when you get to use these later in the period. So it has a constant wavelength, a constant frequency, and I'm going to split it up into two sources. And those two sources are going to interfere, just like the sound sources interfered with each other coming out of this apparatus. Let me show you what I'm talking about, but I've got to turn off the lights. So hopefully you can see the laser beam there on the screen. And I've got to find that. There it is. Now I'm going to take that film that I told you about earlier, and I'm going to put that right in front of this laser so that it's set. Oh man, look at that! Now I'm shining it on two slits, and you can see, I hope you can see, there's bright spots and dim spots. It's pretty pronounced on this one. If I change the distance between the slits there, then I get a different pattern. Let's see if I can find a different pattern. No, that's not good. Ooh, there's a different pattern because the slits are now at different distances apart from each other. But I can still see the dim spots and the bright spots, and I hope that you can too on the video. Ooh, there's another one. Man, that's awesome. That's destructive and constructive interference. And the interference pattern is not just on the screen, it's actually on my hand too, or any place in between. Here's an index card that we can hopefully somewhat see that the interference pattern is everywhere in space here. It's just that it reflects off of the screen and then goes into the camera here for you to see. Well, that interference pattern, whoa! That interference pattern is due to constructive and destructive interference. Constructive where it's bright spots, destructive where it's dim spots. Now I know what you're thinking. You're thinking, there's got to be an equation for all this. And you're right, there is an equation for this. This is an equation you've seen before. Looks like this. Lambda equals dx over NL. It's the same equation as before because it's still a wave. Light waves follow the exact same equations as sound waves or water waves. Again, in this, the lambda is the wavelength. In this case, it's the wavelength of the light wave. D is the distance between the sources. So in this case, it's the distance between the slits. X is the distance between the bright spots from one another, just like before it was distance between loud spots. So you can imagine, you saw that interference pattern looked like a really bright spot, and then a bright spot and a bright spot, and we had those on equal sides. Right? In that case, X is the distance between the bright spots. N is the same as before. It's a counting integer. Right? So that's the, well, here we go. This is N equals 0 in the middle. This dot, or this bright spot, is N equals 1, N equals 2, and so on. And on this side, same thing. This one is N equals 1, the second one N equals 2, and it keeps on going. Then L is the distance, just like before, from the sources to the observation point. So in this case, that would be the distance from the laser to the screen that was here. That would be your L. Now you'll need to use that information when you're doing the home learning for tonight. And one of the things I'm going to have you do with Mr. Winter is I'm going to have you figure out the width of a human hair. You see, the nice thing about this stuff is that this wave interference stuff of light waves, you can use that to find the lengths of really small lengths. If you were to find the width of your hair, you can't use a ruler for that. It's way too tall, it's way too small for that. So instead, we're going to use a laser. And here's how you're going to set it up. You take an index card like this and just cut a hole in the middle of it. Doesn't matter how big it is. That's just fine. Then you take a hair out and you tape it on. I've already got one set up. I know you can't see the hair, it's too tiny to see. But there's a hair stretched across here. Now I just shine the laser on that, and this hair is like, it's the D right there. It separates the laser into two sources, and they interfere. So you'll do the exact same thing I just did. You'll, with the lights off, you will set up the laser. I know you can't see this because the lights are on, but you'll set up the laser, you'll shine that laser right on the hair, and behind me, I know you can't see it because it's too bright in the room, but you'll see it with the lights off. There's an interference pattern that sets up right here. You just need to measure with a ruler these other things, X and L, the wavelength is on the laser, and so on. You have the rest of the period to work on those problems, and they're due first thing tomorrow. Good luck.